This lecture is about unobserved component models and estimation of DSG models. These themes are related since DSG model is an unobserved component model, since the variables in the model are not observed directly. And indeed, quite many concepts in the analysis of macroeconomy are such that they are unobservable. We cannot measure them directly from data, and then these concepts or measures are actually quite important in the design of macroeconomic policies. For example, structural rate of unemployment, potential output gap, structural deficit. These all require that we extract from data something that we cannot measure directly. And how to do this is that one needs to specify so-called unobserved component model and then put it into a state space form and then use Kalman filter to link it with the data and estimate the model parameters. And with similar way, one can decompose the time series to different components, for example, cyclical, seasonal, trend components, and then these sum to the original series. We will study as an example how to decompose a time series to cyclical and trend components. And then when we estimate the DSG model, we need to link the model variables which are unobserved to data, and also for this we use Kalman filter. Okay, let's see as an example trend cycle decomposition as an unobserved component model. We observe from data a log of GDP, which is deseasonalized, seasonally adjusted, and then we can assume that it consists of trend component, cyclical component, and some unexplained variation, which we can call measurement error. Then we can define time series processes for these components, to trend and cyclical components. What we assume here is that trend grows with this growth rate on average, and then cyclical component is a zero mean component and returns to zero according to this raw AR1 coefficient. And then these shocks here drive these processes. The difference to, for example, use linear time trend is that there the trend consists of observed time vector, and then we estimated a parameter to this variable, which was sort of a time vector. There wasn't anything unobserved variables in that approach. This was in the descending lecture note. But now the cyclical and trend component are unobserved variables, but we measure them having this log of GDP observed. First thing to do is to put this model into state space form. And in that form, we have measurement equation where we link these unobserved components to the data that we observe, and then transition equations that determine the evolution of these unobserved components, which are called states. They determine, or they states are the evolution of these series of this whole system. Okay, in the measurement equation, we measure the prediction of states to output, and we assume that it doesn't fully explain the observed output, and that's why there is this measurement error. And then we use these transition equations to measure, to predict future trend and cyclical components. And once we observe the data, then we can update our guesses regarding to these cyclical and trend components. And we do this using Kalman filter. Let's put the measurement and transition equations into matrix form. The transition equations are in so-called companion form, where we obtain, besides these coefficients that we have here, we have this state vector. It includes also the lagged values, and it determines here that this t-1 or t-1 here equals t-1 here. So this way we link these lagged values to this state vector from period t-1 to period t. And when we have this kind of a matrix, it's called companion form. Okay, now we have this in matrix form. And our errors are distributed normally with this variance covariance matrix, where this is actually a scalar, since we have only one variable in the measurement equation and one shock. And now we will use a Kalman filter to recover the unobserved components, the states. We do it so that we have to choose some starting values for the first period for these states. Then we use this transition equation to forecast next period states. And then we use measurement equation to see how these are linked, how our forecast match with observed data. And then we can update our guesses for these states. And then we do this until the end of the data. So let's see this process in more detail. When we have to forecast for state for period t, conditional on information of t-1 is here. Then we obtain period t information, and we get forecast errors using the measurement equation. We get forecast errors for the measurement error for the measurement equation, and see how well our forecast for states constitute the observed series for log of GDP. Based on these forecast errors, we can update our forecast for our guess for states. So now it's conditional on period t information, whereas in the beginning, in the step 1, it was conditional on period t-1 information. So after observing it, we update our states, with this formula where we have this kt variable, which is called Kalman gain, and it's then obtained through this Kalman filter recursion, these equations here. Where we have omega, which is a covariance matrix for forecast errors, and then P matrix, which is a covariance matrix for the states. And then these determine the Kalman gain, how we should update our guesses regarding the states when we observe the observed variable. And as you can see, it's largely depends on, or it depends on these R and H matrices, which are these variance covariance matrices. So in a sense, the precision of information matters how much we update our guesses. How large are these error variances and covariances that determines how we update our guesses for states when we observe the observed variable. These Kalman filter equations, they are derived using Bayes' rule and properties of normally distributed variables. Then we have some parameters here, for example, this row here. Then we have variance covariance matrix parameters, how to estimate these. One way is to use maximum likelihood estimation, where we have maximum likelihood function, log likelihood function of this form, where we have forecast errors similarly as we had when in previous lecture or lecture before that, where we quickly checked what maximum likelihood estimation means. And then we have this variance covariance matrix of forecast errors. And then one simply finds parameter values for model parameters which maximize the value of this log likelihood function. Another way to estimate this model is to notice that these are, so in a sense, they are linear regressions. So conditional on states, one can use OLS estimation for model parameters. And then once one has new parameters, then one can obtain new states, new path for states conditional on these parameters using a Kalman filter, and then having new path for states, one can again re-estimate the model parameters and do this several times until the parameter values don't change anymore. There are many uses for Kalman filter in macroeconomics. One is in the estimation of dynamic factor models, where there is one or few unobserved components that explain much of the variance of large set of correlated macro time series, typically for 50 or even for 100 time series. Then if one uses a dynamic factor model or VAR for nowcasting, then one uses Kalman filter to get the nowcasts, which is basically or usually a conditional forecast for period T GDP growth when one has for the same period some other variables that are published with a shorter publication lag. Then one use for Kalman filter is time-varying parameter models, where parameter estimates are allowed to vary over time. And these parameters that are not constant, they are the states. And then DSC model estimation that we are going to study next. There, the model variables are the states, and then we need to use Kalman filter to link them to observed data. Okay, let's see then how DSC models are estimated. Paper by Smets and Waters from 2003 was one of the first papers that estimated DSC model with Bayesian methods. And before there was GMM estimation and calibration, and then likelihood estimation. But maximum likelihood estimation is quite difficult since the empirical properties of DSC models are quite weak. So there are identification problems such that some parameters change so little the empirical fit of the model that the likelihood function is quite flat, and then it's difficult to find optimal parameters which maximize the likelihood function. Then they are not, the likelihood function of DSC model is not necessarily hasn't kind of a regular shape. They can be uphills and downhills, and then it's difficult to find the global maximum. But then Bayesian estimation and methods offer is that one can use extra information through priors, which then help to identify parameters. And even if this information wasn't useful as such, it helps the estimation process since it smooths, adds curvature to posterior and in a sense regularizes the posterior function so that the estimation is easier than maximizing the likelihood function only. But often quite tight priors are need to use for estimation of DSC models, at least for some parameters. There has to be tight priors to identify these. Or I mean, when the data information is really weak regarding some parameters, then there has to be use tight priors, and hopefully then one can obtain data information from some other data sources. The models that are usually estimated are a bit larger than we have studied during this course, but basically they are new Keynesian models with RBG model stuff that we have studied, and then some extra. But just combining everything into one model that we have studied during this course is all quite close to medium scale DSC models that are used in applied work. There are lots of different frictions, since typically DSC model responses are such that variables respond quickly and then return quite quickly back. But then VAR impulse responses typically are much more hump-shaped, and to generate this kind of hump-shaped impulse responses, these different rigidities has to be included, like investment adjustment costs and price and weights rigidities that we have studied. Usually there are quite many equations, at least if one has an open economy model. Then there are many shock processes, since one needs to have at least as many shocks as has one observed variables in the estimation. There can be measurement errors, but usually shocks that have some structural interpretation also are more preferable. So as an example, typically there are more than 10 parameters to estimate, and then others are calibrated. And if one has 10 observables, then there has to be 10 AR1 coefficients for SOX processes plus standard deviation parameters for SOX. So 30 parameters. If one estimates a VAR for same data of 10 variables with 2 lags in the VAR, this means that there would be 265 parameters to estimate. So when we have a theory model, there is much less parameters than in a purely empirical model. It has pros and cons. One is that it introduces sort of a shrinkage, that there is less parameters, but of course it restricts a lot. And then if this theory that we have in the theory model is not correct, and it cannot be fully correct since these are really stylized models, then it decreases the empirical fit of a theory model, because it has to fit so many time series, but has actually quite few parameters for that. One thing to notice is that DSC models produce stationary fluctuations, but then they are fit to data that are growth variables. So there are at least two ways to deal with this. Is that first is that one filters or detrends the data before estimation, and then uses only the cyclical component as data. Or then one can include, for example, TFP process, which actually has a stochastic growth component in the model, and then one doesn't linearize the model around the steady state, but around the steady state growth path. And then one can link directly the model to either, well, often to growth variables, but it could be it is even possible to link then the model to data that is in log levels and displays growth. So what is needed to estimate the model? There has to be priors for model parameters. Then we link the model to data with Kalman filter, and then obtain log likelihood function, and combination of priors and log likelihood function gives us the log posterior. One first finds the maximum point for it, and then starts to simulate the posterior distribution using so-called Metropolis-Hastings algorithm. That's often used. There are these days also more efficient algorithms introduced. For example, so-called sequential Monte Carlo algorithm. What determines the priors is that for some parameters there are reasonable bounds. For example, AR1 coefficient for TFP has to be greater than 0, smaller than 1. But then just constraining this parameter space is not enough to form a prior. There has to be sort of a shape for the distribution too, unless we assume a flat prior. So we can assume a uniform prior where our beliefs regarding these parameters are such that it's equally likely what value it takes from this interval from 0 to 1. Then we can have a beta distribution which restricts it to 0 and 1, but there's some shape so that, for example, depending the parameters of the beta distribution, it is more likely that the parameter is 0.2 than 0.7, or vice versa if we parameterize the prior distribution differently. Sometimes one can use estimates from microdata to obtain priors for some elasticity parameters, but it's also a bit difficult since then one uses estimates from micro to parameterize parameters which determine macro level behavior. Okay, then how we map DST model to data. So if you recall from solab.r function, when we solve the model, we obtain a solution where state variables determine rest of the variables. State variables are capital or TFP. And then state variables itself are determined by their past values and then shocks. So this is the outcome of a solution algorithm. And solution algorithm that we have used is solab.r. In the beginning, we calculate similar stuff by paper and pencil. But when we have this model in this form, we can forecast endogenous variables given the states of t minus 1. And it is obtained from this so that yt equals f times xt, and then xt equals p times xt minus 1. So this way we can forecast variables from period t by having state variables from period t minus 1. And then when we obtain observation for these yt, we can obtain our forecast errors and then update our guesses on states. And since states are driven by these structural shocks, we can update our guesses for structural shocks. And we use Kalman filter for that. So now we have a DST model linked to data in state space form. This is the data. And here we make a forecast, or we link states. First, we link the states to model variables from here, and with this S matrix, we link model variables to observe data. And this S is only a sort of a selection matrix. It consists of zeros and ones. So it selects which model variables we link to data. Typically, there are more variables in the model than observed variables that are used in the estimation. Then these matrices and various covariance matrices are given by our model parameters, and then one needs to estimate these model parameters, which determines these matrices. And for that estimation, we need to get likelihood function. And we obtain it so that we use Kalman filter to obtain the forecast errors and the variance covariance matrix similarly as with the trend cycle decomposition in the beginning of this lecture note. And then we can form the log likelihood function. And then when we have for each parameter values, we have a log likelihood function, and then we can evaluate prior functions. Then we will get the posterior, which is our target, or what we are evaluating in this process. And then the parameter estimates that maximize this log of posterior, they are called posterior mode estimates. And we need to find them in the beginning of the estimation. And they are different from maximum likelihood estimation parameters, since in maximum likelihood estimation one takes into account only the maximum value of maximum likelihood, whereas in posterior also the prior matters. When we simulated the posterior distribution of VARs, we had analytical expressions for posterior means and variance covariance matrices. Yeah, this was because we had a linear model and then suitable conjugate prior distributions. With DSC model, this is more complicated, since even though our model is linear, these P and F matrices in this, well, here, they are not, they are nonlinear functions of the original model parameters. And that's why we cannot derive distributions for model parameters itself. And then we need to use an algorithm where we can simulate the distributions even though we don't know their shapes or parameters beforehand, or expressions for means and variances beforehand. So we need to take, we don't know the shape of posterior distributions, but we can evaluate numerically for each combination of parameter values. And we do this for many combinations of parameter values to simulate the distributions. And one efficient way to do is to use so-called Metropolis-Hastings algorithm. So in the sense, we are not estimating, we are simply, we are actually simulating distributions, and then from these distributions, we can calculate posterior means or variances. So the process starts by finding the posterior mode and so-called minus inverse of Hessian at the mode, which measures the variance and covariance of model parameters. And this helps to start the estimation simulation. So we start from posterior mode, and we draw parameters according to this equation, where we draw the parameters from normal distribution using this V matrix, which is preferred with the minus inverse of Hessian. And then we have a scaling parameter to determine how much there is variance in this process when we draw, from how large is the variability in our drawing when we draw these parameter values. If the C is really small, then theta star is close to theta. If it's really large, then we move a lot from this previous draw. Okay, for both parameter vectors, we can get values of posterior after evaluating priors, and then log likelihood function. And then we compare these, and if for this theta star, the posterior is higher, we accept and store it, and this is our new theta, and then we simulate the theta star. If the posterior probability is smaller, then we either accept or reject it. And the reason to do this is that if we always reject parameter vectors which has a lower posterior probability, we would stay at the posterior mode. So this makes us to explore the posterior distribution and not staying at the posterior mode, which has the highest posterior probability. Let's see an illustration for this. There is a code. I've written an example MATLAB code where we have US data, US unemployment. Our model is AR2 model, so that the model consists of 2 lags of unemployment and an intercept. As the starting values, we obtain the OLS estimates from here, and then we can run the Metropolis Hastings algorithm. So when we have starting values, we obtain new theta, which consists of these intercept AR1 and AR2 parameters, and then the variance parameter. With this theta parameter vector, we can evaluate the prior probability density functions, which we do here, and we take log. We have assumed 0 mean and variance of 10 for all, so it's really diffuse, a flat prior, so that it doesn't change much, or the prior doesn't affect to this estimation much. Then we obtain residuals, regression residuals, once we have some betas simulated, and then we obtain the log likelihood function. And then we compare these log likelihood and log prior for this new parameter vector to previous parameter vector ones. And then we accept or reject it, like explained in the lecture notes. So we obtain the starting values with OLS estimates, but then we start the simulation just by drawing randomly parameter vectors and then accepting or rejecting some of them. Let's see how this works in practice. Okay, so there are now 2000 throws. and it starts to look a bit like a normal distribution for all these parameters, like it should, since we have a linear model and priors were normal distributions. Now 40,000 draws done. And now we have 50,000 draws done, which was our number of draws for the simulation. And this is the posterior distributions we obtained from this simulation. To obtain more smooth, we would need even more, to obtain smoother histograms, we would need even more, larger amount of draws. Okay, so this is for the 50,000 draws. So we started from the posterior, from the OLS estimate, then we draw some parameter vector, and then we started to reject or accept them. And this shows us all the accepted, histogram of all accepted draws. And if we had this, if we didn't have this B step here, we would never move from posterior mode to these areas where this posterior density function has a lower value. Okay. So this was an illustration for Metropolis Hastings algorithm. Yes, and it was a random walk Metropolis Hastings, since we always change at the point at where we do the simulation. And hopefully this way we will explore the whole distribution. Important thing is to tune the scaling parameter so that it has average acceptance ratio around 0.4, 0.5. Why it is important is that if C is really large, we will explore a lot from the distribution, but then we will also reject quite a lot. If it's small, then typically we are accepting more of the draws, but we will stay quite close to posterior mode. Okay, so these were the elements in the estimation of DSC model. First, you obtain some draw for parameter vector, solve the model with those parameters, link model with the data using Kalman filter, or the model variables to data variables with Kalman filter. This way one can evaluate log likelihood function and priors, and then using this Metropolis Hastings accept and reject algorithm, one either accept or rejects these new draw for parameters. And repeat 100,000 times or 1 million times. Estimation of DSC models requires a lot of draws and takes a lot of time, from hours to days. And we can see an example code for this too. Okay, this is a MATLAB code to estimate the DST model. What it contains is the first, where it downloads the data. It defines some calibrated parameter values. The model itself it's a Smets and Waters model. It's defined in this file. Then we obtain starting values for parameters that we need to estimate. There is a function that evaluates the posterior function to obtain the posterior mode. And once we obtain it, we can start the Metropolis-Hastings algorithm. For that, we need the likelihood function. So we use the SOLAB algorithm to solve the model, and then we obtain these matrices for states and linking states to other model variables. And from these, we then build the Kalman filter, which is here. The notation is a bit different from the lecture notes, but this is the Kalman gain. This is a log likelihood function. And this goes from the first period till the end of the data. And then we evaluate priors with this function, where we have probability distribution density functions for all each variables that we then we evaluate simply those functions, and some log of those functions together. And then this is the Metropolis-Hastings algorithm, where we have similar acceptance reject algorithm as in the previous code. Okay, so these are the parts that one needs to have in the code when one estimates a DST model. Then how to evaluate estimation? One is to check for convergence, so that the starting values don't matter and the simulation has converged to stationary distribution. There are tests for that, and one can also visually inspect the series. Then how to see how well the model performs is to, for example, run out-of-sample forecasting or compare marginal likelihood to other models. Often this is not enough. If one uses model for structural analysis, then also the input responses that the model gives has to be interpretable and reasonable. What one can do with estimated DST model? Well, structural analysis, which means basically impulse response analysis, then one can think that if it's well estimated, then it represents the real world or real economy reasonably well, and then the analysis is trustworthy. Another option is to use DST model for forecasting purposes, and then to analyze the macroeconomy through shock decompositions, historical shock decompositions, so that some path of some variable is decomposed into contributions of different shocks. Then one can analyze, for example, whether, for example, private, for example, the growth of GDP, is it due to domestic or external factors or demand or supply changes or in demand or supply conditions? There are quite a lot of problems in the estimation. The empirical fit is not super good. There are parameters which are hard to identify. One question is how structural are these parameters? Will also parameters that determine the behavior of firms and households change if the policies change, if the same model is estimated for a different period of time when there are different monetary or fiscal policy rules. Then another, and this is crucial for structural analysis, since to make the model useful for testing different monetary policy rules, one needs to assume that other parameters are independent of monetary policy rule parameters. Then one thing is that how structural are structural shocks. Even though we have names for these shocks, it is not self-evident what do they mean. For example, markup shock. Is it a shock which changes the bargaining power of or the monopoly power of firms? And if it's markup shock, wage markup shock, is it something that changes the bargaining power of labor unions or workers? And how this can vary quarter to quarter. Then to compare DST model with the VAR. So VARs are easy to estimate. They fit well to data. DST models not so well. But then to do economic analysis with VAR, one needs to transform VAR to structural VAR. And like we saw, then there is identification issues. With DSC model, one doesn't have these identification issues, but parameters itself are not necessarily well identified because of estimation problems. So these are the trade-offs between the use of DSC models and VAR models.